Hello. Now that we've done the warm-ups, you've checked your answers to the warm-up exercise, let's look at the second page of 1.2 here. We've got a lot of information in these boxes. A lot of it is going to be new words for describing things you've already done in 1.2, which is why I think it's okay to give you this much information at once. But some of it is actually kind of pretty tricky, especially when we get to echelon form. That's going to be a little tricky. So we'll take some time with that. But first of all, let's look at a coefficient matrix here. So we're used to having a system of equations written like this, where we start with equation 1, and there's maybe equation 2 in there, up to equation r, however many equations there are. And if it has c different variables, there's x1, x2, however many in between, up through xc. Those are all your variables. So when you're solving systems of equations like this, sometimes it gets tiresome to write the variables every time, because if you always sort of write it in the standard form where the x1 is always first and the x2 is always second, then you don't even really need to write x1 and x2, right? You could just keep track of what the coefficients are. Like a11 means the coefficient in the first equation of the first variable, x1, and a r1 means still a coefficient of x1, but now an equation r. So if we just keep track of those coefficients and what the constant coefficients are on the other side, maybe we don't actually need to write all those pesky equal signs. So that's what a coefficient matrix does. If we have a system of r linear equations with c variables, it is an array. Array just sort of means a grid of numbers with r rows and c columns. By the way, that's why I'm choosing the letters r and c, because it goes with rows and columns, where each entry in the coefficient matrix corresponds with a coefficient of a variable in the equation. So, for example, all of the coefficients in equation 1 are now going to be row 1 in the coefficient matrix. And all the coefficients in equation r are now the entries in row r of the coefficient matrix. So there's that. A lot of the time, we're going to also be talking about an augmented matrix. That's where we write the whole system, including the constant coefficients on the other side. But the part on the left is the same as it was with the coefficient matrix. We're just augmenting the coefficient matrix with this extra column right here. And I like to write a line here, just that's where the equal sign goes, right? To show that it's a coefficient matrix. I don't think that's really standard notation, but it makes it easier to know that you have a coefficient matrix, and that's where the equals go. So we're also going to talk about the size of a matrix. The size of the matrix you write is the number of rows by the number of columns it has. So this matrix has one column for every one of the c variables, so that makes c columns, and one row for every one of the equations, so the size is r by c. This one has all c of the columns plus an extra one, so the size is r by c plus 1. Now, as far as 1.2, a matrix is basically going to represent a shorthand way of writing a system of equations. But what we're going to do later in the class, I mean, pretty soon actually, starting with section 1.3 and 1.4, is we're going to start studying a matrix as a mathematical object on its own. And the further we go into the class, the more a matrix is going to be like the focus of what we do, and we're going to do more and more complicated things just with matrices. So let's just get some practice understanding this. We're going to look at the system in exercise 1 part C, meaning the warm-up exercise. And we're going to write the augmented matrix of the original system and the augmented matrix of the reduced system that tells you the solution. So the original system had its first equation was 1x1 minus 2x2 plus 1x3 equals 0. So that makes the top row of that augmented matrix. The second equation was, well, it was just 1x2 minus x3, so that's going to be a 1 and a negative 1 in those columns, but there's a 0 x1 that you usually don't bother writing, but you got to write that 0 as an entry in the matrix. The last, oh, I missed the negative 1 here. The last equation was x3 equals 6, so that means 0 x1 plus 0 x2 plus 1 x3 equals 6, like so. Now, there's also the system that tells you the solution. Like, we finished doing all the Gaussian elimination. That was just x1 plus 0 x2 plus 0 x3 equals 4. The second equation was 0 x1 plus 1 x2 plus 0 x3 equals 5. Then we had 0 x1, 0 x2, 1 x3 equals 6. That is a simplified way of writing those systems of equations. Now, these matrices are in a special form called row echelon form for this one and reduced echelon form for this one. We're going to look at exactly what does that mean. What's the formal definition of row echelon form and reduced row echelon form? The gist of it, though, is the fact that if you look at where the zeros in the bottom left are, based on where the leftmost non-zero entries are, and look at what's below that, where all those zeros are, you kind of have this like staircase form of the zeros with these leftmost non-zero things on them. And it's nice to have all those zeros in the bottom left because it means all we have to do is clear away the stuff in the top right, which didn't take long at all. So this is called echelon form or row echelon form. And we'll see exactly how you can tell if something is in echelon form or row echelon form in a minute. It basically means you're close to finding the solution. Now, the one where you're finished, this one here on the right, is called reduced row echelon form. And reduced row echelon form basically means you've gotten as far as possible. You've done as much Gaussian elimination with the system as you can. And maybe as a quick example, like it's not always just going to be like 1x1 equals 4 and 1x2 equals 5 like this. Sometimes it's a little messier. Like if we look at part B here, this one, we've done as much elimination as you can do. Like there's no way to get rid of the 2x2 or the 3x3 at this point. So it turns out that this matrix, or the augmented matrix for this system, is actually in reduced echelon form as well. And it basically means you've done as much Gaussian elimination with the system as you can. All right, so let's see what is the formal definition of this. So we start with the idea of a leading entry. A leading entry in a row of a matrix is the leftmost non-zero entry in that row. For example, with this one, you go as far left as you can, and the leftmost non-zero entry is 1. That's not 0, so that's good. On the second row, the leftmost non-zero entry is this one here, because there's only 0 to the left of that. And then in row 3, the leftmost non-zero entry is this one here. So those are the leading entries. And same thing here. These are the leftmost non-zero entries in the finished system. So we say a matrix is in row echelon form, or sometimes just echelon form, if it satisfies these two properties. Property 1 is that any rows, plural, with all zeros are below rows with non-zero entries. So we don't have any rows with all zeros here, so that was done. But that might matter, for example, in something like the exercise 1 warm-up where you have a row of all zeros. That needs to be on the bottom. So that's condition 1. Just get all your all zero rows on the bottom. Condition 2 is the really important one. It says every leading entry is to the right of the leading entry in the row above. And that doesn't apply to the top row, which doesn't have any rows above it. So let's check that here. This leading entry is to the right of the one above. This leading entry is to the right of the one above. So yeah, that is now row echelon form. And this other one is also row echelon form, but it's like extra row echelon form because it also meets these other conditions. So we say it's in reduced row echelon form if it's in row echelon form and also satisfies condition 3 and 4 here. Condition 3 says that every leading entry is the only non-zero entry in its column. And let's look at this one. Okay, this leading entry right here in column 1, it is the only non-zero entry because everything else here is 0. This leading entry here is not the only non-zero entry in column 2 because the -2 is not 0. So this is not reduced row echelon form. However, here we have this 1 that's the only non-zero entry in its column. This one is the only non-zero entry in its column. These are not leading entries, so it doesn't matter. So every leading entry has to be the only non-zero entry in its column. And condition 4 is easy to check, is that each leading entry has to be 1. And yeah, we have that here. Each of these leading entries is 1. So that's reduced row echelon form. Now, let's look at just to get some practice with this, we're going to skip this definition of row operations and row equivalent matrices for now, so we can just get a little bit of practice with the echelon form ideas with example 2, and then we'll come back to that in a minute. So let's look at example 2. Circle which of the following matrices are in row echelon form, and double circle the ones that are in reduced row echelon form. Okay, so let's look at this first one in the top left. We do have a row of zeros, and is that row of zeros on the bottom below everything else? Yes, so it meets condition 1. Then let's look at condition 2. Every leading entry is to the right of the ones above it. Well, here's the leftmost non-zero entry in row 2. -5 is the leftmost non-zero entry in row 1. And -3 is to the right of -5. So yes, that is echelon form. We do have like a staircase shape here. So yeah, row echelon form. Is it reduced row echelon form? Well, no, because the leading entries need to be 1. And you can't have a 7 here because everything above the -3 has to be 0. All right, so it's not reduced row echelon form. Let's look at the second one here. Okay, so first identify the leading entries. Here's that 1, here's that 1. Everything to the left of those is 0. So they are the leftmost non-zero entries. Now, is the one below to the right of the one above it? Yes. So it is echelon form, row echelon form. Is it reduced? Well, let's see. Both the leading entries are 1, so that's good. And they're also the only non-zero things in their column. Everything else in these columns is 0. So yeah, that is reduced echelon form. Let's look at the third one here. So here's the leading entries. Is each one to the right of the one above it? No. The second one here is directly below the one above it. So this is not echelon form at all. It fails condition number 2. And yeah, if you were going to like try to draw the staircase here, it wouldn't work. You don't have zeros on the bottom left. Okay. So yeah, the fourth one, let's look at this. We have leading entries here and here. And yeah, the -3 is to the right of the 7, so that's good. You can draw the staircase. And so it is echelon form. Is it reduced? No, it's not, because the -3 and the 7 are not equal to 1. So the leading entries aren't equal to 1. And they're also not the only non-zero entries in their columns. So not reduced. How about this one? Okay, so leftmost non-zero column 1, leftmost non-zero in column 2, leftmost non-zero in column 3. There are your leading entries. Each one is to the right of the one above it. Sounds good. So it's echelon form. And also they're all equal to 1. And everything else in each of these rows is all 0. So yeah, we've got reduced echelon form. Looking at the next one, here's our leading entries. Is each one to the right of the one above it? Well, let's see. This one is to the right of the other one. Now, it's not directly to the right, but it's kind of how, like, New York is east of Los Angeles. It's not directly east of Los Angeles. That would be Pasadena or Riverside or something. But New York is somewhere to the east of Los Angeles. So this one is to the right of the one above it. So that is echelon form. Now, is each leading entry the only non-zero thing in its row? Yeah, above and below this one, there's only that one 0. Above and below this leading entry, there's only that 0. Now this 4, can't do anything about this 4. It's not in the column of a leading entry, so it doesn't affect whether it's reduced echelon form or not. Same with this 3. So yeah, this is reduced echelon form. How about this little guy here? It's only got one row, but that's okay. It still has a leading entry. The leftmost non-zero thing is this 1. And there are no leading entries above it for it to be right of, so it is vacuously true that it meets condition 2. And so it is echelon form. Is it reduced? Well, is this 1 the only non-zero entry in its column? It is. Yeah, there's nothing else there. So this is actually reduced echelon form. Now this last one looks a lot like the first one. You've got your leftmost leading entries in the 3 rows right there. But is each one to the right of the one above it? Like this one is not to the right of the top one. So no, this is not echelon form or reduced echelon form. So hopefully you have an idea of what to look for reduced echelon form and echelon form. And the idea is we are going to do Gaussian elimination in the form of these augmented matrices. So instead of swapping the positions of 2 equations, we're going to swap the positions of 2 rows, because each row is really kind of just a different way of writing an equation. So yeah, all of these row operations are the same as like the regular Gaussian elimination equation operations. And we say that 2 matrices are row equivalent if one can be transformed to the other by a series of these row operations. So for example, in example 1, these are row equivalent. I like to write row equivalent with this like tilde symbol, because we could transform the first one into the second one with a series of row operations. And that means that their systems of equations that they represent are going to have the same solution sets. Because that's what theorem 1.1 said, was that doing Gaussian elimination operations does not change the solution sets of the systems. When you do these row operations, you're doing the same thing, just in the form of an augmented matrix. So next, we're going to do an example of writing out, like describing the systems once it's been reduced or partially reduced. And let's save that for the next video. Take a little break. I will see you in a few minutes.